Welcome, hackers, to Attack on Tuesday. My name is Taggart, and tonight we are going to be doing some offensive work. We're going to be diving into an area that, admittedly, for me, is a bit of a pain point. Well, I enjoy learning it, but I'm by no means an expert. I'm definitely still learning this material, and I think it's probably one of the more challenging areas, at least for me, in the entirety of the offensive security pantheon or spectrum. It is, we're talking about reverse engineering and binary exploitation tonight, and those are two different things. We're going to cover how they're different, but it's one reason why it's difficult is because if you didn't have the formal education background to understand the operating system architecture or either the processor architecture that we work with every day on our computing machines, that is a level of knowledge you need to build up in order to do it. The other challenging part is that it's so working against the way that we usually think about our applications. So a couple of reasons why I find it challenging. And one last piece is that it's very difficult to find a lot of solid content available, at least for free, to learn this stuff. Now, I've been trying to compile as much as I can over the last couple of years, trying to get good at this, but it's tough. But there is one resource that I found that I think is pretty solid. It takes some personal discipline to use well, though, and I'll admit that I haven't always made the best use of it myself, but I'm going to try tonight. And so we're going to take a look at the Nightmare course, which is hosted for free on GitHub, and itself brings together resources from all over the internet to one place to cover both reverse engineering and binary exploitation. So let's dive in. So if you want to play along, we're here at guyinatuxedo.github.io. That's our URL for this course. You can also just search for Nightmare GitHub, and it'll come up as the first result. And as you can see over on the table of contents here, there's a lot going on. Lots and lots of challenges pulled from all over the place, different CTFs, right, that they've put together for this course. But it starts with an introduction into tools and concepts. And the first two concepts that are really important here are the difference between binary exploitation and reverse engineering. We gotta change up the music a little bit, I think. I am like never happy with the music that I start with. Let's see how this does. Yeah, all right, that'll work. So, with binary exploitation, what are we doing? We are taking a compiled program, right, not code that we can read, but the compiled ones and zeros, and we are using disassemblers and other tools to look for vulnerabilities in the way the code was written. Depending on what functions in certain programming languages that are being used, there may be vulnerabilities available, or simply just programming mistakes that the programmer made when creating the program that we can use to our advantage to execute certain kinds of attacks to get the program to do what we wanted to do, not what it was intended to do. And then reverse engineering, which is part of binary exploitation, is taking that program back up from those ones and zeros and looking at kind of a reconstructed set of instructions, either in assembly or going up even higher into a facsimile of the original programming language to understand exactly what it does and how. And so, generally speaking, the objective of reverse engineering or binary exploitation for sure is to obtain code execution. That's the offensive version of this, pop a shell. Reverse engineering, especially in the fields of malware analysis, that's much more about understanding how the program works and, in many cases, looking for a way to stop it from working. So there are a bunch of different kind of prerequisites if you're coming at this cold. One of them is knowing some programming. Now, I will admit that I am not a C programmer, and I have tried really hard to get away without knowing. No traces here, Commissioner. We have to find it. I have tried to get away without knowing a whole lot of C programming. Now, I've learned some more actually in the process of learning reverse engineering. Maybe we'll switch it over to some chill stuff. A little bit nicer. Yeah, that'll work. So, if you don't know C programming, that's okay, because neither did I when I really started doing this. But knowing some programming is really going to help. Understanding the concepts of variables, functions, loops, things like that, because that's what a program is made of. And as we reverse engineer these things, that's kind of what we're going to be looking at. There are also some tools that we're going to end up using. I will be using different ones, perhaps, than the ones listed here. I will not be using GDB. I'll be using an alternative disassembler. But I do have Ghidra, and we may use Ghidra. We're also going to be looking at a bunch of different CTF challenges. So hopping around all these, as many as are still around and that we can use reasonably. And I like this rationale here. He said, why CTF challenges? The reason why I went with CTF challenges for teaching binary exploitation, RE, is because most challenges only contain a small subset of exploitation knowledge. With that, I can split it up into different subjects like buffer overflow, into calling shellcode, and fast bin exploitation, so it can be covered like a somewhat normal course. Makes a lot of sense. I like that from a pedagogical standpoint. So in terms of environment, the course author recommends an Ubuntu VM, and that makes total sense. I am going to be actually doing this pretty much in Windows Subsystem for Linux, and so it is an Ubuntu VM in practice. But and I'm just doing that for processing speed, really, and ease of access to other stuff. I have my Kali VM up. I could do this in the Kali VM, no problem. Same kind of deal. Okay. The other thing I'll mention, it's actually even more of a prerequisite, I would say, than knowing C, is figuring out assembly. Now, if you've never read any assembly, x86 assembly language, it's going to be really difficult, if not impossible, to perform this at first. And it takes a long time to get used to reading the CPU instructions written in assembly code and what they mean in terms of what the program is doing. I've been at this a little bit, and so I can ask where the bathroom is in assembly, right? I can't carry on a full-on conversation. But one of the ways that you learn how assembly works is by starting off with a compiled language like C here, and then, watching what happens when you disassemble it. And we'll actually do that first, just so we have that kind of on record. And I kind of want to do this in C and then maybe do it in Rust just to see the difference. But let's start here. So let's vim hello world.c, right? And we'll do exactly what this is. We'll just do a little copy pasta here. Right, so what are we looking at? We're looking at including the standard IO library, the headers that contain that information, right, for doing puts and reads, things like that. And we create our main function, and we're writing out hello world. That's it. Let's compile that down into our executable binary with GCC. We'll call it hello world, and then we give it the source code. Now you see I have a hello world binary there. If I do file on it, it tells me it's a 64-bit LSB. Nah, I did it for 64-bit. I should have done it. Yeah, M32. I have to give GCC a flag of M32 to have it compiled to a 32-bit executable. No! Alright, I guess we're not doing that. We'll just leave it as 64 for now. I don't know how much of a difference it'll make at this point. But if you wanted a 32-bit executable, that's what you'd need to do. I think I'd have to download the 32-bit headers to make that work. Okay, so now if I run Hello World, right, it works. It does its thing. It doesn't do anything interesting, but it works. Now, let's see what it looks like in assembly. One of the easiest ways to do that is with objdump. And let's look at the help for objdump. It has a bunch of stuff that it can do, right? A lot more than I use. We do objdump hello world. We'll do objdump-d for disassemble. And yeah, okay. There's one other thing that I want from the objdump options, and I didn't see it. Oh, -m. Intel. Much better. So this is what the assembly looks like. And the way to read this is kind of... I know it's a lot. The way to read these tables is you kind of have your address in memory. It's a virtual space, but you know, your address in memory. And then each of these rows has kind of a start number. And so how many bytes later are we in the instructions? So right, so we start at 1000, and then 1, 2, 3, 4 bytes worth of information, and then we're now the first byte of the next row is byte number 1004, right? Or 1004 in hexadecimal. And if we think about these are bytes as well, which is why they're described in hexadecimal so cleanly. Now, these are the byte representations of the instructions, and then here are the representations of the instructions in assembly language. So that's kind of the columns that you're going to see a lot in disassemblers, right? You'll have the address in memory over here. You'll have the byte representation of the assembly, and then you'll have the assembly representation of the assembly. Now, this isn't what the CPU reads, right? The CPU is reading kind of these zeros and ones as they come in, but for human readability, this is what we have. And there's a lot that goes into even a basic program. You can see that we're looking at all of this just to create the program. And a lot of this is kind of the preamble for programs on x86 architecture. Only here do we have the main function. And it doesn't really look like much. It doesn't make a lot of sense as to what's going on, especially if we don't understand these instructions. The big idea that you have to remember with, I guess, 3 basic ideas with working with assembly is the parts of the computer that we're dealing with. The first one is the CPU, and the CPU, of course, is doing math, but to store information temporarily as it's working, the CPU has registers that stores up to 32 bits of information in a 32-bit processor, or 64 bits of information in a 64-bit processor. And think of them just as slots, right? And you can move things in and out of those slots. That's what registers are. And so when you see these move commands, you're seeing these RBP, these are names of registers, right? And this is kind of like a destination source syntax, right? So we're moving whatever value was in the our SP, the stack pointer register, over into the base pointer register, which are special, and we can talk about those. But these are the registers that you have. Now, R is a 64-bit register. That's a little bit deeper than we need to go into now. But these registers are important in how the assembly works and how the program executes. So registers are concept one, the slots of information the CPU is moving things in and out of to make the code work. Concept two is the stack, which is the set of working memory in RAM that the program is using. And the stack, all of the memory is addressed, as we've seen, just like we have here. The stack is controlled by pointers to different sections of it, and that's what the stack pointer does, and it changes throughout and the base pointer, as a matter of fact, changes throughout the run of the program. And so as different functions are called or different parts of the program are set up, information will be moved onto the stack, moved off of the stack, and that has to be the right size in order for the operation to function as intended. And then finally, there's the heap, which is a section of storage set off as well in another part of memory that can be used for calculations for, arbitrary saves of state, things like that, that don't necessarily have to be removed as the stack frames the sections of the work that the program is doing change. Hopefully that was something like a coherent explanation. But this still doesn't look like it makes a lot of sense here. And that's, understandable. One of the things that I like to do with the assembly is not just do obj dump, because that's not really the tool that I use. I will use another tool called radar2. But actually, radar2 has been forked, and there is now a tool called Ryzen. And with it's a little bit newer, and the developer's a little bit kinder. And it's also the backing of the GUI for this called Cutter. So you can actually see Cutter actually has a Windows install candidate. Let's fire that up just so we can see it. I think that might be cool to use. I will extract and install Cutter. While that is working, let me show you what the disassembler looks like just on the command line. So I would do R2-A for hello world. And what that does is it loads up the program, it disassembles it and analyzes it. So it gives me all this information. And you can see that I have this new kind of command prompt. This is a set of instructions that I would have to learn. It's very much a language unto itself, much like a Vim. And if I press question mark and enter, I get kind of all the potential instructions that I can give it. And the way that radar2 or Ryzen work is that these instructions kind of chain. So you can see that I is for information. If I do I question mark, now I have all the I commands that I can ask for. Things like the imports. Right, so it looks like I'm importing these different functions, the puts function, right, the libc start main, things like that. I can ask for symbols, which is is. These are all the symbols, basically named sections of the program, including, there should be a main in here somewhere. Yep, there it is. And that will be kind of our entry point. And actually, IE will tell us what the entry point of the program is. It tells us that we're at 001, the address of 1060 in hex. That's the entry point. And you'll notice that that's actually where radar2 has put us in the program, is at address 160 or 1060. If I were to use the S command, which is seek, and seek for the function or the symbol main, it does change me to someplace else though. Because let's look at what the 1060 does. there isn't really a function here. Not really. It's the start main part of libc, and then we have to get kicked over to the main function, which is at this address. And if I use P, which is print, and D for disassemble, and then F for function, so I'm printing the disassembly of the function at this address. What? Cool, so glad this is working. Let's look at those symbols again. Yep, there's the main. If I do PD, what does it show me? Not much. Concerned that this isn't working the way that I would have expected. It's interesting too, because you can see that I do have, this is where the call to puts happens, and there's the hello world string. So there is some stuff in here that is working correctly. Let's try cutter. Let's see how well cutter runs. So cutter is a GUI for Ryzen, or Red R2 is what it used to be. I would like the dark theme, please. Ooh, what's the midnight theme? That's a little bit darker. Okay. So let's open the file here. We have it in our learning. And I made a nightmare folder. There's the hello world file. Okay. We're gonna analyze it. How many Star Wars things are there? All right, let's fire this up. And we get a lot more information. Kind of see the map of the memory space here. Pretty cool. There's our functions over here. There's main. So this worked just fine. I don't know why the Radar 2 in WSL didn't work the way that I expected, but you can actually see that in Cutter, oh, good. There is a zoom. That's handy. And in here, we'll have the memory address. We'll have the instruction. And you'll also notice in Cutter that you'll get a little bit of C flavor in some of the comments. You can see this int main. Right? And that's exactly what we have going on here, which is main takes an integer argument of the count of the arguments to the program, a vector of potential of characters for other arguments, and then the environment variables, right? And so the rest of this is kind of the preamble getting this thing ready. And we'll start here where we're pushing the base pointer, whatever the base pointer happens to be, onto our stack where we're storing information. Oh, that's neat. That disassembly preview is cool. if we move the stack pointer, remove the base pointer onto the stack, saying, okay, this is where we're starting our program. And then we also move, we push the base pointer onto the stack, and then we also move the base pointer's address into the stack pointer register, because the two of them are at the same place. And then we're loading the effective address, that's LEA, of whatever in this register here, which happens, or into DI. Whoa! We're loading the effective address of this, and then that's kind of it, because it's such a simple function. So, or such a simple program. So we call that, and we go into sim.imp.puts. What's sim.imp.puts do? Let's take a look. Oh, that's so cool. Cutter also has a decompiler, which we'll get to in a second. We'll see how that goes. But with the puts function, what do? So we have to jump actually to this section here to see what it does, because this is an import. Yeah. So relocating to there. So puts is a libc thing, so we don't actually have it really in here. We'd have it in libc. But that's okay. What we can infer for the moment is that, let's get back to our actual main function. Is that it moves the string into the AX register, the RAX register, which is the output, and then the syscall sends it to standard out, and then we end our program. So it's kind of how we're looking at this, and I'm really liking Cutter. This is actually the most that I've used of it. Let's see what happens if I show this in the decompiler. That rules. Look at that. So this is the pseudocode. You can see how it's reproducing the C for us. We didn't write this, it wrote it for us. Very cool. I also love this when there's a graph. We can actually see the graph of the functions and how they relate to each other. Right, this is our disassembly. We can also see strings. So Cutter is really, really powerful, and you can kind of see why. Even more so than the R2 that I've been killing myself trying to use. And isn't working as well as I'd hoped. So we might use Cutter a little bit more than I thought today, which is fine. I'm impressed by this. This is pretty cool. All right. So if you want to get Cutter, go ahead and go to cutter.re. Really, really nice. And I feel better that I'm using Ryzen rather than R2. All right. So we'll leave Cutter open, but let's also show the kind of the other option for disassembly decompiling, which is Ghidra, and this is actually from the NSA. It was leaked and then it was open sourced, but it was from the NSA. And so let's take a look at Ghidra. Let me fire Ghidra up. Yes, I agree. I gotta move all of this stuff over, all these windows that Ghidra creates. So Ghidra is project oriented, so create a new project, right? And I like to put these kind of in a single place. Like so. I'll call it Hello World. And then from here, we import files. So I would import, actually, from that learning folder and Nightmare. There's the Hello World. I would import that. Okay. Format raw binary. That may be why it's not working. It's definitely in C. There we go. It's x86-64 GCC. This is our... Okay. Interesting that it couldn't figure that out for itself. All right, let's see how that does. What we're going to do is we're going to fire this up, and we'll see our little Ghidra Dragon. And the code browser is going to come up. Not what you want to see. All right, well, that didn't work nearly as well as I had hoped. And that might just be because of the program, like the way that I compiled it, right? I might be the problem here. Yeah. So we'll see if we can use Ghidra to better effect on another challenge here. And then lastly, the other tool that we're going to be using is Pwn tools with Python. So it's a library of utilities written in Python to make CTF stuff, but also just binary exploitation way easier. And I deeply love Pwn tools, so even if we can't get the stuff in WSL to work this way, I will definitely be using Pwn tools in here in my trusty IPython window. And if you need it, just go ahead and do sudo pip3 install Pwn tools, and we'll work on, you know, some of what you can do with it. There's a lot to Pwn tools. You can even do debugging directly from it. All right, with the tools and basic concepts out of the way, let's try some basic stuff. Some of this might be a little too basic. Yeah, we don't need the strings. We've done the strings command a bunch of times on here. Although it might be useful to see it in a reverse engineering context. Let's go check out picoctf. Now, I have an account here. And we'll turn on just the reverse engineering stuff. Is it also binary exploitation? So what was this? I think it might be considered like a strings. Yeah, let's see what we have here. Can you find the flag in the file without running it? I think this is going to be closer to what we want. So let's save this link. into our nightmare. It's called strings. I'm going to call it pico strings. And let's run file on this thing. File pico strings. Okay, so it's a 64-bit executable, right? Now, of course, we can just run strings on this thing, and I usually like to give it a maximum or a minimum length of 8, right? And we'll get all that. But take a look at some of these. These may look familiar to what we were looking at inside of our disassembler. Now, I'm going to try root_r2 again just to see. Okay, so this one, I was the problem. This one disassembled just fine. So you can see that I have a bunch of strings here. I'm not running it, I'm just disassembling it. But even in here, if I do inspect and then Z for search for strings, I don't want all 9,200 lines. That's worse. So I can get the strings even though there's a bunch of them. But if I print out this main function again, I may actually be able to see a little bit more information. So I'm puts something. See that puts? I'm printing something out again. What am I printing out? Putting out. Well, the first thing is maybe try the strings function, right? So this whole program, all that it actually does is say, maybe try the strings function. It doesn't actually ever print out the string in question. So we'd have to go look for it. Now, one of the things that's pretty cool is that you can use command line tools right in R2. So one thing, I do like Cutter, but I do love the command line flexibility of R2 Horizon here. So glad that it's actually working and I can stay in my precious command line. We can see that I got this, it's in the data section of the binary, and then it's ASCII information, and there's our picoctf strings it. So we can look for ASCII strings inside of a binary, and very often that can be revealing, right? If somebody has hard-coded some sort of secret in there and references it later in the code, that can be discovered with this really, really simple technique. All right. Moving right along. Hella Thumper. The goal of this challenge is to get the flag. This was a challenge made by Hella Thumper. Let's take a look at the binary. Now, we don't have a direct link to it. And we don't know which one of these things it is. Yeah, we don't know. And this is one of the problems I've actually had for a long time with Nightmare, is that the links to this stuff are actually pretty poor. Now, these are maybe discussions, but nevertheless, I want to be able to do the thing. And I can't do that if I don't have a direct link to the binary. I can search in, this repository for Rev. Maybe I'll find something, but that's really not the best way to do it. So what's this challenge trying to teach us? We got to get the flag. And it's not written in a string, so we have to figure out some other way of doing it. Let's see if there's another challenge that'll help us out like that. Or we just cut over to Seesaw 2019. These are all write-ups. I don't want write-ups. I want the challenge. Am I missing something here? Is there like an appendix? No. So it's just all referencing material that we can't actually access anymore. That's a little disappointing, and one of the reasons why I've struggled with this so much in the past. Okay, may have found it. There we go, we got Beleaf. Fantastic. Let's actually download this entire thing. Well, let's download Beleaf, because that's the exercise we're dealing with here, so. And we're going to just download the binary for now, because the whole point is to try to reverse it, right? Without looking at the source code. So let's take a look at it and see what we got. File Beleaf. It's a 64-bit executable. It is executable. Let's run it. Enter the flag. I don't know. We got to figure out what the flag is by reviewing this source code. Let's try it in Cutter just for accessibility. And also because now I'm excited to play with it. All right, so we will select Beleaf. Off you go. Okay. So those are our types. Let's look at our strings. Here's our list of strings. Now, it doesn't appear as though there are a whole bunch of strings that are like immediately, obviously, our flag, right? There's all these kind of tiny strings here, which are a little bit strange. We're not sure what that's about yet. And then we have our imports. But let's go to our disassembly. We'll look at our main function. So what do? We have some declared variables, which is interesting. Now, the way that Cutter or Radar 2 pulls these is that it's looking at every time the the variables are declared up here, and we're setting up the stack to use them. So we have kind of, if we go down here, oh, there's a stack canary for preventing binary exploitation. But so argc and argv, right, they're set up, we know those, but then we also have other variables that are declared inside the code, and they're set up like this, right? We have this S, we have uint32 set up here, we have a size, an int64, an int64, and another car. So these are variables that the function is using. We don't know what they do yet, we just know that they're there. All right, here we're setting up the function. We're kind of setting up the base pointer and the stack pointer, right? We're setting them equal. And then notice this right here. We're subtracting from the stack pointer the x0, xc0, which I'm gonna bring up IPython and from pwn import everything, just because we'll use it. But what's cool about this is we'll do some just hex conversions with this, right? So we're subtracting 192 bytes from the stack pointer. And the way that the stack works is that it starts at a high address and moves to a lower as it grows. And what we're doing is we're making space for all of the variables that we're going to have to hold on the stack during the execution of this function. And if you look at the way that the variables grow here, you can actually see that work. So you can see, okay, well, we've got argc, rv, those are set to their own registers. They don't matter on the stack. The canary is on the stack though, and then after that we have at 0x90 back from the base pointer, we have this variable, and then 8 more bytes back we have this variable, and then so you can see we keep going kind of up and up and up and up, right, as the stack grows with those variables. So what we're doing first is we're moving the stack pointer up to the top of that to make space, right? So the base pointer, right, stays here at the bottom, then the stack pointer comes up here and will eventually come back down here. Okay, we've seen this before, right? The load effective address. Get out of here. Load effective address. Can I turn that off? Yeah, we'll not worry about it now. But so we load the effective address of the string enter the flag, and we put it in RDI. Then we call printf. It's a little bit different than puts, but the same kind of idea happens, where we are basically printing out that string. And then we come back into this function. So we go into that function, we do whatever that needs to do, and then we come back here. Okay, then we load into RAX this register, whatever S is. And we haven't seen it other than to see that it's this variable here, right? Now, it's probably the case that S is where our secret is. We don't know what it is yet. Okay, so we load it into RAX. Then we move the whatever is in RAX to the RDI register. So now whatever was here is now in RDI. And whenever you see a move or a push or sorry, an add or whatever, it's always destination source. That's kind of the syntax there. Then we call another function called strlen, which compares basically, or it gets the string length. It doesn't compare. It gets the string length of whatever we're looking for, and it happens to be, oh shit, what is up, everybody? Oh my god. How's it going, all? Welcome to the party. Good to see everybody. For those of you who've not been here before, my name is Taggart. Sorry about the let me chill Nightbot out a second. I turned it off. Oh, excess emotes. Yeah, it's off. There we go. So, for those of you just joining us, which is a bunch of people, we are going through, as best we can, the Nightmare Reverse Engineering and Binary Exploitation course. And if you want to check it out for yourself, let me throw that in chat. Thank you all for the follows. Kachalimbu 0xA79, Thordev, FDS 101, Cologne Panther, Kachalimbu. We're going through this now. This is a very gentle introduction, kind of, to binary exploitation and reverse engineering. No, this is not Nightmare on Hack the Box. Sorry, y'all. That's right. Sorry to bait and switch on you there. And what's a little bit tricky with this course material is that a lot of the links. Oh, does it really? That would make sense, because a Rob chain exploit is a nightmare for me. Yes, Isloveni, I did, because I'm a viewer. Actually, I'm a subscriber. Yep, this is Nightmare on GitHub. Good to see you, Chad. But one of the challenging things with this particular course is that the source material is kind of all over the place. And as much as I love the instructional material that's written here, the links to those things are not there. So you got to do a little bit of detective work to go find them. So we just found the Seesaw 2019 belief binary, and it's kind of what we're poking at. The tool that we're using to do so is Cutter. And now that I have more of an audience here, let me give a little bit of my pitch for Cutter. MS4202, Eslaveni, Socialist Maker, thank you so much for the follows. And I think I missed one. 99XGG, also welcome. So there are a lot of different disassembly options out there. You've got Ghidra, right? You have IDA Pro if you are rich. But I really like Cutter for a couple of reasons. One, it's cross-platform. Two, it's based on the Ryzen disassembler, which I think is very, very powerful. We were using that in the command line earlier. And it just kind of has everything that you need out of the box and nothing you don't. So it really just gets to the point of, hey, show me how this program works, show me how the assembly works, and then if you really want to, it actually has, on Windows at least, with when Ghidra is present, it uses the Ghidra decompiler. So you get a decompiler. Look, it's C, it's not assembly. So you get all of that out of the box for free with, I think, a little bit less overhead than Ghidra. Ghidra's amazing, but I don't know, I find Cutter a little bit more ergonomic. Also has a handy dandy graph view, which I really appreciate. I'm zoomed in a little bit. Ghidra is chonky. Yeah, and I mean, just look at this. This is what you want to see, right? Very much like if you're used to IDA, it has a similar view to that. Very easy to see program flow. Yep. And as always on this stream, if if I can, I'm going to show you free and open source software, which is exactly what this is. All right, so this one's pretty simple here. What are we doing? Let's go back to our disassembly. So the idea with this program, actually, Cutter, let me throw that link into the chat, cutter.re. Yeah, no problem. It's funny too, because I had no money when I was starting to study this stuff, I was like, everyone's like, oh, you gotta go get IDA. No, I cannot afford that. And so I ended up like really forcing myself to learn all of the arcane commands of, let me go to learning, let me go to Nightmare. This is what it looks like on the command line if I do R2 of belief. And I do like AAA for analysis, seek main, PDF to print out the disassembly of the function. Like, I have the same stuff on the command line, but all of those commands were so arcane that, you know, I forced myself to memorize them. So now they're like stuck in there, and I will use this most of the time. But for ergonomics and for demo today, I'm trying out Cutter. It's the same disassembler engine, just without the nice GUI. So what this belief function does is it asks us to enter a flag, but we don't know what the flag is. Now, what we do see here is we're looking at this call to strlen, and it's getting the strlen, it looks like, of S, because strlen uses whatever's in the RAX register, and that's what's moved into RAX before the call. Or actually, no, it might use RDI. Sorry about that. But either way, right, we're getting that S variable, whatever it is. S is, according to our notation here, some character variable or character pointer that lives at this position on the stack. So, well, once we have strlen, we'll have some information in RAX. And we're going to move that quad word into this variable position, whatever that is, right, from RAX, which is what we get for strlen. And then we're going to compare it to this number, this scalar value of 0x20. What is 0x20? Well, I don't like to do that comparison in my head, so I just ask IPython for it. It's 32. I could have probably figured that one out, but the point was to show IPython, which I find to be an indispensable tool when reverse engineering, or really anytime. So we do that. So we compare, and then we do a JA, and JA, I believe, is jump at, right? Do I find it handles things like big and little endian well, John Denorris? Good question. Yes, perfectly well. When you load it up, you'll get some information about the binary. It'll tell you whether it's set to little or big endian, and it'll just, like, you deal with that, right? And you yourself may have to remember that when you're creating shellcode or something like that. But yeah, nope, handles it just fine. JA is used for jumping if the last flag changing instructor was on unsigned numbers. Oh, jump means jump if carry flag is unset and 0 flag is unset. Okay. Interesting. Show me JA. Jump if above. That's what I thought it was. So JA is jump if above. So if it's greater than 32, right, we're going to head over here and then do all this stuff, right, which is where we want to be. It has to be bigger than 32. Otherwise, something that we don't want is going to happen, which is we're going to load this string into the RDI register, right, which is just incorrect. And then we're going to use puts to print that out. And we're going to exit with a 1, which is the status code here. And then the program ends. So we don't want to do that. So if we don't want to do that, we know that we have to give it a flag that's 33, basically. 33 bytes in length. And then if we do that, the rest of this works. Whatever this is. All sorts of more fun stuff here. Yep, there's the correct, right? And then we call it puts, and then we kind of like end the program eventually. But we want to get to here. So a couple of ways that we can do this, right? The easiest way, though, is to actually debug this thing. To do that, interesting. I have not done this in Cutter, so I'm going to be learning along with you here. What I want to do is set a breakpoint. And I want to set it right here. Breakpoint. Add breakpoint. Okay. Now let's run this. Yeah, let's start the debug and see how well this works. Okay, it does not have executable permissions. Want to bet? Maybe that's because it's in Windows. Oh no, I'm missing X on everybody else. Let's try that again. Boo. Let's close it then. Have to close all the windows. Let's just quit it and reopen Cutter. No. Any objections if I just do this in the command line? I think it's going to be a little bit easier. So I'm going to do R2-D for debug and give it bleaf. And then let me show you how the run works here. We'll just run it as normal. So we're going to seek to the main function. Ooh, it says cannot find function because I didn't analyze it. Let me do the AAA to analyze it. There we go. Now I have it. And from here, I'm going to do the same thing. I'm going to do the compare right here, as long as it isn't too arcane. I'm going to try, yeah, let's try it in the GUI. If I can't get it to execute in the GUI, we'll try it in R2. Analysis enabled. Do not load in write mode. Great. So 0xA79. Yes, this is the R2 or Ryzen is the disassembler underneath Cutter. That's right. And not to get too into the weeds here, but there's Radar 2, which was the original disassembler, which is what R2, that's what the R2 binary comes from. And then Ryzen forked it for like political reasons, but ones that not like the Ryzen folks believed in universal healthcare or something like that, but it was that basically the R2 community was pretty toxic, and so they decided to like get away, and because these were the developers that also were doing the Ryzen GUI, or sorry, the Cutter GUI, then they kind of just brought that along with them. Husky Hacks, Is the 32 byte check on an argument, or what is being checked exactly? It's, yeah, so when we run the program, let me run it in here because it's loaded. Enter the flag. That is the check right here. It's reading this in and checking to see if it's the correct length. Yeah. And we'll bring that up in disassembly here. So if we kind of walk that back, we compare this var A0H to the integer 32, right? Where's that A0H coming from? Well, it's coming from basically the result of this strlen, and strlen is getting called on whatever comes in from scanf. So, yeah. All right, let me try to put I want a breakpoint right I want a breakpoint right here, actually. Ah! Because I want, yeah, right here. Breakpoint, add breakpoint. Wonderful. And I'm actually going to add another breakpoint right here before we do the length comparison. All right, let's see what happens. All right, sorry, we'll do this. We'll do this in the command line. So I'm analyzing, and then at PDF. There we go. So I have the same stuff, and I'm just gonna essentially put the breakpoints where I want them. Same deal, where we call strlen, and then we do that comparison here. So I'm gonna put the first breakpoint at this address. To do that, I do db for debug commands, and then db is breakpoint. And then the next breakpoint I want is, assuming that we get the right length here, right, we're looking for var A0H. So I'm going to put another debug right here. All right, so let's try this. DC is, so D again is the debug commands, and DC is continue the execution. So I'm going to DC, rerun it, enter the flag. Okay. So I'm going to put in a short. This is why I like to have IPython up here. The middle white window is burning a hole in your head. I'm so sorry. Better? Actually, tell you what. The reason it was a split window is because I had the Nightmare course material over on one side. No, hey, same page. Dark mode for life. Absolutely. I was just trying to split the window for multiple content. Watching the input strlen is it goes into RAX. Exactly right. So what we're going to do is we're going to make a 32... Actually, I'm going to make a 31 byte string and copy that. Throw that... Oh, no, what happened? Okay, we hit the breakpoint at this position. So where are we? We're at this position right here where we're comparing, right? Now, what should happen is that we're gonna miss this JA. We should end up getting incorrect and just exiting, which is exactly what happened. This time, let's give it a string that is longer. Okay. Bob, no problem. Thank you for asking. Yes, this is something that you can follow along with. What we are doing is this is why I had it up. We're doing some exercises from the Nightmare course on GitHub. Let me throw that in the chat again. And in particular, we're pulling an exercise from the Seesaw 2019 challenges. And let me throw that in here as well. We're reversing this particular binary to try to grab the flag out of it. Now, I have just downloaded the compiled binary. I have not downloaded the C code or the challenge.json because I don't want to cheat yet. I should be able to get this one. All right. So we've got the 33 bytes here to get us past that 32 byte check. And we hit the first breakpoint, which is good news, right? So we're still at this B90A breakpoint. That was our first one for the comparison. If all goes according to plan, we'll get to, and I'll do a step to see if we get to the 912, and then what should happen next is we should get to 92A. If all goes according to plan. So DS is to step over or step into would be D. Yeah, so DS. All right, we get to 912. Good so far. 92A. So we went to the right addresses, which means we bypassed the length check, so we're on our way. Now, obviously, a bunch of A's is not the flag. So I'm gonna DC to continue until I hit the next breakpoint. And I do hit the next breakpoint. I'm here. Now, why would I want to stop here? Anybody in chat know why I'd want to stop here? Next instructions have criteria for the next jump calls. That is true. There is also another reason why I want to stop here. This CMP, that's right, Alhazred, thank you. Dude, you're the one who took this course before. You don't get to put your hand up. Yes, we can debug and modify variables to make the comparison work. That's absolutely right. You're a professional pen tester, man. I do blue team by day. This is all for funsies. Yeah, so this comparison, basically what we're looking at here, we're comparing whatever's in the RAX register to this Q word, which is a quad word, right? At this location. And this A0H is a location back from the stack pointer. Or sorry, from the base pointer. So what we can do is we can analyze the stack as it is written into memory right now, and from there find out what the flag is. So that's why I wanted to do that. Let's take a look at some of the other debug options I have. So DR will print the registers. So DR, I get my registers, which is cool to see. And you can actually see that I have the base pointer there and the stack pointer. You can actually see that the stack pointer is AE. It's a little bit lower as an address than the base pointer, right? Because remember, when we build the stack frame out for our function, it starts at a higher address and moves low to make that space. So that's where we are right now. And the IP, this is the instruction pointer where we are currently. Look familiar? Right, and these are all, again, registers. These are all just places where 32-bit slots, or actually 64-bit slots as a matter of fact in this case, that the CPU has to hold on to information as it does its work. But what we can do now is take this address for the stack pointer and use it to print forward, or the base pointer to print back. So if I px, so p again is our print commands, and px does a hex dump. If I do px and then an at and do like rbp, actually I want to do rsp. So what we'll see here is that we're getting some of our stack, and look at all those A's, right? That's what we put in. So we know that we're getting some of the information that's on there. Now, problem is, there's our input, absolutely. Now, let's print that function out though, again, and think about this A0H. What is this variable that R2 is named for us? It's right here. It's at the base pointer minus 0xA0. It's pushed right here. And what we can do is actually tell RUDR2 or Ryzen to px at that location. And what we get looks like an exclamation point and a crap ton of null bytes. But that's in part, let's see. Yeah, it looks like just an exclamation point and a bunch of null bytes. Let's see how we're doing on that thinking. That appears to be what it is, but I'm not certain. We could, but to Al-Hazred's point, since we're debugging this thing, we can also kind of live change the values up. If we wanted to, we could actually write into this memory and change whatever the flag is to our A's if we wanted. We could also do the other and change whatever's in this to whatever the flag is. But if I'm trying to discern what the flag is actually supposed to be, kind of looks like this. Question, would the flag var not just exist as a reference string somewhere in the assembly or decompiled code? Not necessarily. It depends on how it was stored, right? If you're referencing a stored string, then yes. But if it's stored in some other way, if it's created in some other way, then no, it may not be. Is that only because it wasn't compiled with stack protection? That's a good question. I'll be honest, I don't know. Stack protection in terms of non-executable stack, it's not that so much. You may know more about what stack protection does than I do. But it's also like, we're not... Let me give another example. So if we look at the way that the strings for incorrect and correct are loaded, you can see that it is referencing these symbols here, right? The strings that are saved, and they're saved at a specific place in the data section of the binary. That's not really what's going on with the flag. It's stored in another way. We don't have the decompilation. I mean, actually, we could. We just have the disassembly here. Let me go get the... Right. So we don't know what this var98H is other than it's a uint32. Right? And that actually is interesting. We also could have figured that out from the function used to read the input, that we're talking about an integer of some sort. Because anybody remember what the function was we used to load the integer? Or load the input from the user? Yeah, it's a good question. I don't know. I don't know what's up there. Yep, scanf, isoc 99 scanf. And if we look up what that is, it returns an integer. So I must be missing something because I'm not seeing an integer in the right spot, right? So we're comparing to A0H. And it's definitely at the right place. 0xA0. That is absolutely... But here's the thing. It's not... Okay, I got a little bit turned around. It's not actually... This is the ASCII representation of the value, but that doesn't mean it's an ASCII value, right? It could very well just be... Right, 21. 21 in hex, right? So 33. Wait a minute. That's the length. Are we still comparing the length here? We are, aren't we? There's no stir comp anywhere in here. There's no use of the function stir compare. Because, let's see. So this is where we are right now. We do... Where were we before? We compared stir len, right? We moved the RAX, which is the result of stir len here, into A0H, which of course, or 33. Did it jump past the move RAX? No. And then, so it compared, and then we jumped. Wait, var 90H. What's at 90H? Another integer. No, these are good questions. Keep them coming, A79. Really, really good questions. I'm a noob too. That's why I'm doing this. This is, essentially trying to learn in public, which is, not something I'm always very good at, but I'm trying to be better about admitting that I don't know stuff. We're all learning. But, so, was that... Yeah, let's at 0x90. Okay, so that's where we stored that. And we're comparing it to a length of 33, so... Okay, so... Chat, we don't know each other that well yet. I used to be a teacher, so... This is, I'm learning, but I want to learn with you, so please don't hesitate to ask questions. I will do my best to answer. If I don't know, I'm going to tell you that I don't know. Try to find out. So, 99, if you have any questions, anything I can clarify, please don't hesitate to ask. What we are trying to do is we're trying to... How often do I use board analogies in class? Well, I used to teach middle school and high school, so not a lot. Although, actually, I guess the closest I would ever get was when I was an English teacher, I would always get the question, when, like, how long should my paper be? And I hate that question. Like, how many pages should my paper be? I don't care about a page count. I care that you answer the question appropriately. You know, if you can do that in a page, dope. If it takes you 5 pages, okay. So what I would always used to say is, like, your paper should be like a dress. It should be long enough to cover everything, but short enough so you're not tripping all over yourself. All right. All right, so as far as I know, we're still comparing it to 33 here, which is what this and what's an RAX? Oh no, we missed that, right? We skipped it because we went right to here. So we're comparing what's in RAX, which is this 0. Okay, well, that's not going to work out. To what's in A0H, which happens to be 33. Now, let's just run this. Okay, great. We had an error. Let's run it again. It's still signal stop error 11. That's interesting. At 218. Because it's not a number. The error is that it's not a number. Oops. I think you can. I think you just have to do it right. So basically, yeah, I was gonna do 33s. Or basically, like, I'm gonna try. What? 31, 2, 3. Yeah. I'm having the hardest time with this debugger. It does not want to stay alive. We're in a different part of the memory now. We get to this address here. Some of these binaries can be used to mask, like a mask to modify other values. Oh, interesting. At this point, I'm actually going to look at the course material because that's what we should be doing anyway, and see how we're doing. I don't want to look at the source code. This actually isn't as helpful as I thought it would be. Starts off by scanning. If our input is less than 21 bytes, the code exits. So our input has to be 33 bytes. Looking at later, we see it enters a for loop. It does. It does. Which we also could have seen through the graph. right? So this is where the graph view comes in real handy. At this compare, this is the first length compare, right, for 33 bytes, right? If it fails it, that red line, then we just hit to, we just exit, right? If it passes, then we move here, we jump to 99D, then we compare the RAX to the keyword, and we jump below. Wait a minute. Oh, it's JB. So we do the compare, right? And A0H we already saw was 33. Now JB I'm pretty sure is like a less than or equals to, but let's find out for certain. Where's my JB? Jump if below. No, it's jump it below 33. So 937. Oh, but this is the loop right here. This is the loop right here. Oh, duh. I'm so sorry. I didn't know what I was looking at. This graph really helps clarify it. Okay, so once we get to this part here, we're moving 0 into this 8H, right? And then we pop down here. Now, this is essentially a while loop. That's what we're looking at in the assembly. Because we move into RAX, that value, which we know is 0, and then we compare it, right? And to whatever our mask was, which was 30, not mask, but our maximum, which was 33, right? So this is where it's checking byte by byte, okay? That's what's going on. Once this value, right, while I, right, like while I is less than, once those two are equal, right, then we get out of it, right? So the JB is kind of, because it's jump if below to 937. So the second this is no longer true, right, we're going to go over here to correct, as long as we're going through this loop. But while it's false, or actually while jump below, while this value is less than 33, we are going to do this. And what is this? We have the decompiler of it. Oh, good, it's math, my favorite. So we're doing multiplication, it looks like. So we load in the string to dx, and then we... Weirdly, I think it's going to be easier for me to look at this in the assembly. Never thought I'd say that before. Computer, enhance. Man, look at that font rendering. I'm so used to the terminal, it's so crisp. Okay, so we load the S, whatever it is, into RDX. Then we move 8H, which is A, right? 8H I thought was where it's 0. Oh, that's all just crazy now. But I thought that was our input, which was A's before. Actually, let's do that again just so it shows up clearly. and we're looking at 8H. I thought I moved 0 into that variable before the while loop. I'm sure you're right. Let's before the while loop. So you are absolutely correct. Yes, it is 0. So we're zeroing out RAX as well. Absolutely good call. Okay, then we add 33, I think, to whatever this is. Oh, but wait a minute. Move keyword var 98 to RAX. I'm trying to get away without having to do all this math in our head because I don't want to do it. If we just skip ahead to the part where it compares, but I think I don't think we get to do that. So we compare, we do all this stuff, we do all this math, we call a function 7fa, whatever that is. We move. Okay, then we jump. Good God. This is the first exercise? No wonder everybody has trouble with this. Well, I don't know that the function, that the output is our flag. See, we're in the for loop here where we're doing something to every byte of our input. And so we like do stuff, and then at the very end, we compare whatever's in 98H to RAX. And if it's equal, we add, we increment by 1. And if we don't, we exit. So unfortunately, maybe look at the decompiled output for the called function to see if it has any recognizable features. Very good call, Husky. And that's what we're going to do. That looks flaggy. While var h is not equal to -1. Right. RAX equals this string. If EDI is less than EAX, then otherwise. the thing is, there's no flag here to really print out. You know what I mean? So the other thing that we can do, not to cheat this beautiful reverse engineering exercise that we're doing, but the other thing we can do is, let's go back to that graph of main. Yeah, A79, mine too, friend. There was a reason I was an English major. But here's an interesting thing that we can do. There's no like print out the flag. You know what I mean? Unless there, I guess there is, because you're trying to figure out what this is. You have to try to guess what the flag is. So I suppose there is a bit of that. But before we get there, we can cheat a little bit. Because we can basically... If we want to just get it to print out correct, we can make that happen. By changing this jump right here to a different command, or a different opcode. If all we cared about was getting it to print out correct, then we could do that. Yes, A79, you're absolutely right. It cycles through our input to produce the flag. The problem is we have to figure out what it's doing at every step, because if we don't, it's going to exit. Yeah, Husky, that's exactly what I was looking for. A place where it compares RAX to a value to print the flag. But the problem is that it doesn't compare. It doesn't compare to the flag. There is no the flag. It is a procedurally produced flag, which is created byte by byte. And actually, the question was asked earlier, why can't we go find the string stored? This is why. Very often it is stored in an algorithm like this so that you cannot just find the simple flag somewhere. And that's what's going on in this situation, right? This is the decompiled main. So we have if var98h is if var98 is not equal to rax, we put incorrect, right? That's the okay. Here we go. So 8h equals 0. Then while rax is less than a0, so this is our maximum, right, which is our 33 bytes. All right, here's our while loop. Then we set up the rdx is equal to the reference to the string, whatever it is. This is our flag, right? Yeah. And don't get thrown by the RAX versus EAX situation. What we're looking at is 32-bit registers versus 64-bit registers. The R's are the 64 bits and the E's are the 32 bits. It's the same register, just less of it. RAX equals var 8h, so that is 0, which we saw up here. Then we add our dx, which is whatever value we've put in. I equals x. Whatever this s is. And it's stored. The s is throwing me off too. Yeah, we add them and multiply them. The trick is, what is the S? Coming up here, it's a character pointer. S is our input. Yeah, that's what I thought it was too. I just want to make sure. RAX equals. Okay, so, all right, so then RX is, I feel like these operations are almost flipped, right? Because for the way we usually do these assignations, because we're saying here that whatever this variable is, it actually should be RAX, yeah, right, shouldn't it? That the S is equal to whatever's in RAX after the scanf. So these are like flipped, interestingly. But this one is. But then we're assigning RDI to whatever is in RAX. See, I was thinking that the decompiled output having the variable needs to registers is very weird. It is, but now you can kind of see why they do it. Let's look at this in... So the S isn't doesn't show up in... See, in Radar 2, they're all integers. Now one of them might be car pointer. No. It's right after the canary. Right here. So R2, not the decompiler, thinks that it's an integer, which makes a ton more sense. I don't think that the S is our input. I think it's a reference, but it's not actually our input. Because if I understand what's going on correctly, so printf, enter the flag, then we load up whatever is RAX. This is actually zeroing it out, I'm pretty sure. Then, and we can do this we can debug it and find out what RAX is at these different points. But then once that happens, we run scanf. Now, whatever scanf does, we don't have the input for it, unfortunately, but scanf is going to put its result in RAX, right? Standard in. So then it makes perfect sense that after that happens, this variable, right, at A0 is assigned to whatever is currently RAX. So I don't think S is that. I think S is some other value. And we should figure out what that is because it's integral to this operation. Calculus pun unintended. Okay, so to figure that out, yeah, to the debugger. So what we're going to do is, yeah, and track S down. Let's go to the graph here. So S is an address. Oh, so it's at the 0x90. I really wish they just call it the 0x90. Yeah. All right, I have breakpoints here. All right, I'm going to put a breakpoint. where are my breakpoints? That's the first one, right? When we load that. Where's the second one? That's good. So I'll be able to access it here because it's loaded at this point. All right. Husky, I'm so glad you do. I'm still learning it. I want to be good at this. It feels like the secret knowledge to me. Okay, we're at this breakpoint. Now, the 90 variable should contain whatever S is at this point. So see, that doesn't seem right because that's just our A's. Wait. I might have misread that. We load S into that's exactly right, Husky. I agree. The instructions are always doing exactly what they say. Also, I like the feeling of being so close to the metal. I like getting a real understanding of what the machine is doing when it's executing my code. There's no abstraction, right? This is exactly, how the information is moving through the silicon. Okay, so here, what the graph shows us here, right, is we have the scan, then we load REX from whatever S is here. Then we move it. That's pretty weird. We are supposed, no, that can't be right. Where is this initially set? What is happening? I gotta add another breakpoint, I think, like right away. Like right here. Oh. Okay, here's why I did that. So we're at 990A. Hey. actually wanted to put a breakpoint right at the beginning, basically. There we go. Ah. Went too fast. Did it again. Okay. Now I'm getting punchy. I'm right up here. And so I want to know, before we do anything, what is this? Yeah, it's nothing, right? It's not a thing, because we haven't moved the base pointer at all. Okay, so now we are... Okay, we should be at AC. Okay, now let's try printing out with the... Okay, so now the base pointer has stuff, but it's 0 at the moment. There's nothing interesting in there. So at this very moment, this value is 0, but it's the effective address. That's the thing with LEA. It's not like load the value. It's a little bit trickier than that. Oh, snap. That might have been why I was having so much trouble. I was reversing the order. So moves go destination, comma, source, right? But LEA doesn't do that. Load effective address. Well, loads the value, but I was reading it backwards, if I understand. The LEA instruction places the address specified by its first operand into the register. So actually, LEA goes source destination. Right? The contents of the memory are not loaded. Only effective address is computed and placed in the register. Okay. So with that information, this is going to start to make a little bit more sense. Right? So here, right, we load the effective address that's in RDI. That doesn't make any sense. We don't load it to the string end of the flag. Or do we? No, this has still got to be destination, comma, source. Address specified by its first operand. Oh, God. Is that first? It's little endian, right? So it is the first operand in bytes, but not when you read out the opcode. If we look at the disassembly of that, actually, do I have it in R2? Yeah, so if I see the load effective address, it's gonna say, yeah, 48.8D, and then so that's the LEA opcode, and then first is still place the address specified as first operand. Nope, it's still definitely not its first operand, even in the bytes. Reading from left to right. But whatever. It's plainly source destination in the way that we're reading it, so that was a bit of a red herring. All right, let's go back to our notes here since we're theoretically learning. Looking at it later, we see that it enters into a for loop, which we found. It will run each character through the transform func, which we didn't get to have named. This is very nice. This is not what we saw. transform funct input I if transformed input is not equal to long typecast of the desired output plus I times 8, then input incorrect. Okay. So our input probably has to be 33 bytes. Yeah, we know that. When we compare the output of that function stored and transformed input against the corresponding character in the BSS array. Talk to me about the BSS array. Desired output, which we don't see. Characters are stored at an offset of 8. This thing had debug flags that we did not get. If the two are not equivalent, exit is called and we fail the challenge. We can see the contents of desired output by double-clicking on it. First output has to be equal to 1, second has to be 9, third has to be 17. All right, let's learn about BSS arrays, because I don't know what that is. Well, I know it theoretically, but right, the block starting symbol of the object file. And so what this is doing is it's looking up this thing in an array, but we don't get this information, basically. So A79, yeah. Each iteration we extract a value out of the array and eventually build our flag. Problem is, we don't see that anywhere here. Yeah, we don't. Okay, so our E0 is the BSS. Yes, and function 007FA is the transform function. That's absolutely correct. Yep, that's what this is. The part that's confusing is where the BSS array is coming from. But that's got to be this. Let's move REX word add where that value is. Now we have an add here. And if we look at the decompiler, there's that add right there. Then it's multiplied. Times whatever the pointer is. Okay. So if I understand what's going on here, at this point, we just got to add a breakpoint to this compare, right? Because, and then very, very carefully rewrite the code, so, or rewrite the values so that, yeah, exactly. Do it for every iteration. I'm learning it too. You know, it's interestingly, the addresses that Cutter did are much simpler, right, than the ones that R2 did. So it's kind of confusing. But I think I want to be here. 98H. $937. Here we go. This is the part where I want a debugging breaking point every time. Okay. So 976. And what we're trying to do is compare whatever's in var 98H to whatever's in RAX. Yeah. Okay. We'll put the 33 bytes in because it doesn't matter. Uh-oh. We got to 218 and we died. Oh, sorry, that was really dumb. Anybody know why we got to that instruction and then died? Pony Lover, how do you learn to read assembly? I have a book recommendation for everybody, actually. This is literally the first hacking book that I ever bought, way before I was ready for it. But eventually I got ready for it. This is the book. John Erickson's Hacking the Art of Exploitation. This is also great if you want to learn a little bit of C from the security perspective. So what it does, it comes with a CD of examples if you have a disk reader in your computer anymore. But I think the code is available online, like on GitHub or something. But this will walk you through the basics of understanding what's going on in a binary when it runs, and it'll have you write your first C, use GDB to debug it and disassemble it. Really, really powerful. I love this book. It taught me a lot about how to even approach this. So if you want to get started, this is where I would start. Okay. The reason why that died was because scan expects something it can turn into a number. And we didn't give it that. So we're going to give it that. We're just going to give it 33 nines. So that Okay, we're waiting for breakpoint 976, remember? Oh, it died again at 218. What is going on here? Maybe I'm not getting even that far. Whoa. I'm getting an instruction that shouldn't be there. Okay. I'm going to reopen R2. And let's try to fix the... So this is the comparison we want to stop on every time, right? All right, so we're going to put a breakpoint there. And let's go to work. I'm wondering if I'm like overloading the value. Oh, I probably am, right? That's probably too big. Let's just do a bunch of zeros. Because I think we were doing better with zeros. Uh-oh. And I can't debug in here, right? Ooh. Start emulation did something different than start. All right, that didn't work. Doesn't have executable permissions. Is that because... I swear to God, this is because I'm doing this in Windows. If I were doing this in Linux, it would be a lot easier. Have you heard of skid stops with certain type of result computers because the emulation doesn't actually stop where you want it to? No, I haven't heard about that, but that's interesting. All right. Well, friends, I think I'm going to have to call it a night here. I'm sorry we didn't have a lot of success here, but hopefully we got a good introduction to some of these tools, and I'll be playing with this a little bit more. I'm not going to give up on it. I want to get this, but I'm out of time for tonight's stream. So thank you, everybody, for hanging out. Really appreciated seeing you. Thank you so much for the follows. Let's see if I can send you all someplace fun. Oh, Chad is streaming. Okay, we'll send you to Chad. All right, take care, everybody. Be good to yourselves. Be good to each other. And I'll be back tomorrow night doing some programming. We're actually writing a text-based adventure of backdoors and breaches, Black Hills Information Security's incident response card game. So if you want to see us write some Python more successfully than we were reading assembly. We'll see you tomorrow night at the same time. All right, take care, everybody.